All right. So we finished talking about the importance of the atmosphere in terms of atmospheric pressure, okay, on Friday. But we got to also look at its importance in the absorption, reflection, okay, of incoming solar radiation. We want all the shortwave stuff to get blocked or scattered by the atmosphere so it doesn't come down to the surface of the earth because it's harmful. Okay, the long wave stuff that can easily get through the atmosphere. Okay, that's where heat waves are, infrared light, things like that. Okay, that gets through the atmosphere and gets to the ground. It is absorbed by the atmosphere on the way down. That warms the atmosphere. Anything absorbed by the surface of the earth warms the surface or the water or whatever happens, excuse me, to be there. And that is where essentially the energy that gets things going on Earth comes from. Okay, so that light that gets all the way through, okay, when it strikes the surface of the Earth, it could be reflected. Okay, some of it's going to get reflected, some of it's going to get absorbed, some of it's going to get used. Okay, what are the only things that can use sunlight directly? Plants. All right, so that's going to start the process of photosynthesis, which will start all the chemical energy food chains, okay, food webs and things like that that are present on Earth. Right, so that will start the kind of chemical energy cycles that go on. Okay, the absorbed thermal energy is what's going to get all the other kind of warmth and things like that going. Okay, so the atmosphere plays a critical role in maintaining the Earth's temperature. If it wasn't for the atmosphere, Earth would be very, very cold. Okay, it wouldn't be able to retain any heat. The greenhouse effect is important. Okay, if we didn't have a greenhouse effect, Earth would be unlivably cold. Okay, so we have to have that greenhouse effect. Those greenhouse gases are important. Okay, obviously we don't want it to get out of control because if it does, then Earth will become too hot. Right? We have two examples of that on either side of us planet-wise. Okay, Mars, which has basically no greenhouse effect and is frigidly cold. Okay, and Venus, which has way too much greenhouse effect and is hotter than the inside of your oven on the self-cleaning cycle. Okay, yeah. In fact, Venus's atmosphere, I think I told you guys, is 100 times more dense than the Earth's. All right, so if you were at the surface of Venus, you would be crushed. Okay, in fact, the atmospheric pressure on the surface of Venus is greater than the greatest water pressure you could experience in a submarine, okay, on Earth, right? That's how intense it is. And it's ridiculously hot. Ours is perfect. We live in what's the Goldilocks zone, okay, where everything just kind of works out. So the amount of energy, solar energy, that gets absorbed by the surface of the Earth is determined by this, the albedo. Okay? Albedo refers to the reflectivity of the Earth's surface. Something with a high albedo reflects lots of light. Something with a low albedo absorbs lots of light. So dark colors have a low albedo. Light colors like white, okay, have a high albedo. So right now, the ground is covered with snow, which is white, okay, and it reflects away a lot of the incoming solar radiation that we are getting, the pathetically small amount of it that we are getting right now. Okay, the sun is low on the horizon. We're only going to see it for 7 hours today. Okay, it's not giving very much, and what is there, most of it is being reflected off by the light-colored snow. So if you see a comparison here for a place like where we live, okay, here in Okotoks, in the wintertime, okay, 85 to 90% of all solar radiation that arrives on the surface is reflected away. Okay, so none of it basically gets absorbed. Right? Then there's this 10 to 15% that actually does get absorbed. Right? That would be by the surface of plants maybe that are poking through, or that are like pine trees or things like that that are still dark in color during the winter. But for the most part, it gets reflected away. Everybody follow on that? Okay. Now, are there things that we do to change the albedo of things like snow? Okay. Yeah. Okay. When the salting and sanding trucks are driving around after a snowfall, okay, they're throwing sand and salt onto the road. All right. The sand lowers the albedo of the snow and ice, meaning it will now absorb more solar radiation. The salt will lower the melting point, raise the melting point, okay, of the ice. Lower the melting point of the ice. I said that right the first time. Lower the melting point of the ice because we want it to melt more quickly. Okay, so not only are we having something making it darker so it absorbs more energy, but we've got the salt in there to help it melt earlier, okay, and get rid of the snow and ice off of the road. So that's the reason we do that. Okay, we don't just throw salt on the road. That doesn't do any good. Okay, we need something there that'll help to darken it so it'll absorb more solar radiation. In the summertime, the situation is almost completely reversed. Okay, we have 70% absorption because now the surface is darker in color. Plants are there, they're carrying out photosynthesis. Okay, 10% would be reflected off of, like lakes and things like that, and about 20% would be reflected off other surfaces that just happen to be somewhat reflective. Okay, this is of course all dependent on what does the surface of the Earth look like in this place. If it's a dark color or covered with lots of plants, lots of the light gets absorbed. If it's lighter in color, more gets reflected. Not always. I mean, it depends where you are, right? Some surfaces absorb better than others. Okay. At the equator, if there was a lot of water, okay, with high angle sunlight, a lot of that gets reflected away. Okay? Some of it goes through and gets absorbed. But really, it doesn't matter whether you're at the equator or the poles. It's more what's the surface look like that determines albedo. Okay, everyone follow on that? Okay, it's like if you have a dark colored car and a light colored car. Okay, on a hot sunny day, the light colored car you might be able to put your hand on it if it's been sitting in the sun all day. But if you do that to a black car, it's going to be really hot. Probably won't be able to hold your hand there very long. Okay, how many people have ever seen those like camp showers? You can buy them like Canadian Tire. It's just like a black bag with a shower nozzle or a hose coming out of it. You just hang it in the sun. Okay, it's a reason it's black. Right? We want it to absorb lots of solar energy. You can actually get the water in there to, kind of a tepid, okay, or kind of lukewarm temperature. You're not going to get it hot, right? But it's better than taking a cold shower with the creek water. Okay, but it does work reasonably well. That's why it's dark in color. All right, so albedo, that's something that's going to be important. Okay, it's a term that comes up all the time. And we see here the role of the atmosphere in what it does with light. Okay, we got the backscattered light that makes the sky blue. We've got reflection by the tops of clouds because obviously the tops of clouds are white. Okay, we've got some absorption by water vapor and gases that would warm the atmosphere. Okay, and then we've got stuff that gets absorbed by the Earth, reflected stuff that goes away, and obviously some of that would be returned by the greenhouse effect. Okay, which is kind of our next thing here. Okay, we got solar radiation coming in, getting reflected away by the atmosphere, absorbed by the surface and reflected away, stuff that's trapped by the greenhouse gases, okay, things like that. Okay? And our greenhouse gases, like we said, maintain our temperature, okay, and keep our climate the way we want it. If they get out of control, then obviously the greenhouse effect will increase, and then we could have things like global warming and stuff like that. Okay, so carbon dioxide. Obviously the most well-known and common greenhouse gas. Okay, CFCs are a greenhouse gas. Methane is a greenhouse gas. Where does that come from? Farts. Yeah, cow farts. Yeah, anybody's farts. Okay, that's methane. Okay, ozone. Okay, nitrous oxide and water vapor, believe it or not, is also a greenhouse gas. Okay, so all of those things contribute to the greenhouse effect. Okay. Yeah, so we all know what the greenhouse effect is, right? We don't need to go over that in too much more detail, right? But it's important in terms of it's a role the atmosphere plays in trapping energy and maintaining climate. Okay, the hydrosphere includes all the water on Earth, okay, including water vapor, right? Including the stuff that's already been evaporated. So it's not just the liquid water, it's solid water, so it's ice and snow, okay, as well as water vapor. It essentially includes anything that might be part of the water cycle at any one point. Okay, less than 0.1% of all the water that's evaporated from the surface of the Earth actually gets returned to lakes, rivers, or streams, or seeps into underground hollows. Where does most of it end up? In the ocean. Okay, and conversely, lots of the water that evaporates from the ocean ends up on land, okay, when it falls as rain, because obviously that's the biggest storehouse of water for evaporation and keeping the water cycle going. All right, so the water cycle, you've been beaten over the head with this like every other year, basically throughout your whole science career. Okay, well, one more time. We're looking at it from an energy point of view, not so much from a evaporation, precipitation, all that kind of thing. Okay, we're still looking at that part of it, but we're looking at it more in terms of where's the energy going? To evaporate water, either from a liquid source or from the surface of plants while they carry out photosynthesis, requires what? Energy. Requires sunlight, requires energy. Okay, now, where does that energy go when the water evaporates? Yeah, it's stored in the water vapor. Okay, energy has to be absorbed by water for it to change state. Okay, we call this latent heat. We're going to talk about it a lot in this unit, but I'm introducing it just a little bit today. Okay, we call it latent because you can't sense it. Okay, water vapor is in the atmosphere right now. It's in the air surrounding us, but it doesn't feel hot. Agreed? It's a good thing. Okay, but it's this latent heat. Okay, so when this water vapor now is in the atmosphere, it's got a whole bunch of stored energy in the atmosphere. When that water vapor moves around and goes from place to place, it can bring that energy with it, sometimes over great distances. Okay? If we're talking about like the snow that we're supposed to get, okay, in the next couple of days here, okay, that moisture has to come from somewhere. Okay? And when it does, it's bringing the energy it absorbed and turning from a liquid into a vapor, okay, with it. Now, most of it's, of course, going to be lost in the upper atmosphere, okay, because it's going to turn to snow, but it's still going to come with it. Okay, so that latent heat is going to move over to another place, and when this stuff evaporates, or sorry, when it condenses and falls as precipitation, whether it's rain or hail or snow, the energy is then released. Okay, so we're transferring energy from one place to another through the atmosphere, okay, by this process. So this is an energy transfer mechanism. And it's a huge one that gets overlooked a lot. Okay? And this is part of what can drive like big storms and things like that, is all this latent heat that's present is now being released, and it can drive the formation of winds and all kinds of things. It becomes other forms of energy when it gets released from its latent heat kind of form. All right, so we get all that stuff falling onto the earth, okay, and some of it's obviously going to run off and make its way back to the ocean. Some of it'll get trapped in lakes and wetlands and marshes and bogs and things like that. We call that freshwater storage. Okay, some of it will absorb down into the ground. Okay, that's important because it recharges things called aquifers. How many people have heard of an aquifer before? Okay, an aquifer is what we tap with a well in order to get drinking water. All right, town of Okotoks uses wells for most of our drinking water. Okay, I know a lot of people think that we draw all of our drinking water from the river. Honestly, guys, the Sheep River is tiny. If we drew enough of water to supply all of Okotoks from the Sheep River, it would be dry downstream of Okotoks. Okay, it simply does not have the volume of water to supply all of our needs. We take a lot of stuff from wells that are recharged by, okay, the river, wetlands, okay, and things like that that are in the area. Okay, so that process, which is called infiltration and may not have been taught to you previously, okay, as part of the water cycle, infiltration, okay, is the process of water essentially percolating down through the soil in the same way that water goes through coffee grounds when you make coffee. Okay, it just trickles through and ends up and collects in these aquifers. Right? Now, an aquifer is not an underground lake. People get this vision of these underground hollows filled with water. It's not like that at all. Okay, an aquifer is actually more like gravel with water in it. Okay, so the water fills the spaces between the rocks, and there's just a big, dense, kind of gravelly, rocky area where, okay, we can draw a lot of water from. Okay, it's more like that. All right, and then obviously some water can be trapped, okay, in frozen in ice caps, glaciers, okay, things like that as well, which is then going to be slowly released. All right, so most of the Earth's water, 97% of it is saline, okay, salty. It's in the ocean, can't be used for drinking. Okay, only 3% is fresh, and most of that 3% is frozen. Okay, so it would be present in glaciers, ice fields, okay, polar ice caps, both of those places. Okay, about 1/4 of the available liquid water, okay, is known as groundwater. That's the stuff we pull from aquifers. You can kind of see that in this really poor diagram down here. Okay, you can see that there's wells being driven down into the aquifers and having water pulled out. Okay, so we got our salty water, we've got water flowing on the surface, rivers, lakes, things like that, and then we've got obviously the stored form of water here, okay, solid ice. Now, what's happening to our glaciers? They're melting, okay? I mean, and they're naturally melting. The world's been getting warmer for the last 10,000 years. Okay, if you go back like 10 to 15,000 years ago, and you were standing right here, you'd be under a kilometer thick sheet of ice. okay, called the Laurentide ice sheet. Okay? It has been receding for about 10,000 years. Right? So this whole idea of glaciers receding and shrinking is not new. Okay, we're worried about it for sure, and we have good reason to be. That's where a lot of our drinking water comes from. Okay, but it is a process that is occurring naturally. Now, is it accelerating? It might be. Okay, it might be accelerating due to what we're doing. Okay, but it has been going on for quite a while. The main concern here, guys, is that by the time we started to notice, these glaciers were already pretty small. I mean, imagine this used to be part. This single small glacier used to be part of that giant ice sheet that stretched all the way to the Great Lakes. Okay, that's how big it used to be. Right. So, I mean, yes, they've been shrinking for a long time, but over the last 100 years, we've been kind of more watchful of them, and it's a bit alarming actually to see just how far they've gone. This particular one is the Robson Glacier, and when you stand at the toe of it, okay, you can see kind of the whole thing, and then there's kind of clear mountain and alpine meadow and whatever below it. We were walking up towards it, and we came across this sign that's just kind of planted in this little meadow. You can't even see the glacier from where this sign is. And the sign says, in 1902, the Alpine Club of Canada marked the toe of the Robson Glacier at this point. We walked 1.5 kilometers before we got to the toe of the glacier. Okay, so in 100 years, it's receded 1.5 kilometers. Okay, now that's only one dimension of the shrinking. That's length. What is it also shrinking? Height. Yeah, its volume is also shrinking. This glacier used to fill the whole valley. Okay, so it's not just how short it's getting, it's also how much less volume it has in total. So it is something we need to watch. And of course, anytime you get more rock exposed, what happens to the albedo of the ice? It gets less, so it absorbs more energy and it melts faster. Okay, having all these dark rocks around the edges also means more light's being absorbed near the glacier, so it's going to melt faster. When it was one big giant gleaming blue-white ice sheet, okay, it didn't absorb very much energy because it was very clean. Right? If we have dust storms and things like that that deposit dust onto its surface, then it melts faster. Okay, so if we have a few years like the last 2 years, the glaciers recede a lot in these past 2 years because they didn't get as much fresh snow deposited on their surfaces to protect them from the sun. All right, the lithosphere. So the lithosphere doesn't play a very big part in transferring energy. Okay? The hydrosphere plays a big part because of all the latent heat that's present in the water cycle. But the lithosphere has hardly anything to do with moving energy because it's the solid part of the Earth. And energy doesn't move through the solid part of the Earth very effectively. That's why the Earth's core can be very, very hot, and on the surface here, we're fine. Okay, the hot part of, like the mantle and things like that, we're insulated from it. The Earth doesn't transfer the heat from below to the surface. Okay, conversely, if sunlight strikes the lower parts of the mountains, it doesn't transfer up the mountains to the top through the solid rock. Okay, that just doesn't happen. So the solid part of the Earth doesn't play a big part in transferring energy, but it plays a big part in the absorption of energy, and it provides the place where plants can grow. That's its main role. Okay, the lithosphere is important in the use part of of what happens to light. Light's reflected, absorbed, or used. Without the lithosphere, there'd be no soil for plants to grow in, and there would be no conversion of solar energy into chemical energy. So that's kind of the importance of the lithosphere. Okay, so soil is the topmost layer of the Earth's surface. It's a layer in which plants grow. Soil is an ecosystem that contains biotic and abiotic components. We talked about those back in the biology unit. Abiotic are the non-living things, biotic are the living things. Okay, looking at this picture here, how would you describe this soil? Yeah, that's what we would generally say, right? It's bad. In fact, some people would go, that's not soil, that's rocks. Well, there's a plant growing in it, so it's soil. Okay, the topmost layer of the Earth's surface is soil. Some soils are better than others. Soil is different everywhere you go. Where does soil come from? From rocks. The erosion and weathering of rocks is what builds up soil. That's why on the tops of mountains and things like that, like here, this is kind of the top of a valley, okay, Most of the soil, anytime there's wind or rain, gets washed away. The small particles get washed away. What's left behind is rock. Okay, and that's what we see on the tops of mountains. Okay, those rocks are weathering, but the products of that weathering aren't being caught and kept there. They're being washed down into the valleys where a thicker soil builds up. Okay, so soil is typically divided into horizons. When you were a kid and you dug a hole, okay, you probably noticed that there were layers, right? There was like the dark dirt, and then there was clay, and if you dug far enough or you were in the right place, you might even have started hitting rocks. Okay, like I know where my house is, the bedrock is, there's an outcropping of it, and it's really close to the surface. When I tried to build my fence and put my post holes in, I dug down this far with the post hole auger and hit rock. Okay, so yeah, I got a lot of concrete on my post holes because they're not very deep. Okay, but in most places, at least around here, most places, the soil is quite thick. Okay, because we live on the prairies, and prairies typically have very thick topsoil. So, okay, topsoil is what we call the A horizon. Don't worry about this organic layer. We kind of include that in part of the A horizon. Okay, so the A horizon is where decomposed plants, dead insects, fecal matter, all that stuff that's on the surface is present. And that's all the stuff that is present for plants to grow because it contains nutrients and oxygen. Okay, this part is usually really good at retaining water, okay, things like that. Underneath is the B horizon. That's the subsoil. That's usually clay. Okay, clay ends up on the bottom because clay particles are very small. Right, so like when you were a kid and you had your sandbox, right, there always seemed to be clay. If you dug down through the sand, there was always clay underneath. Guys, when you build a sandbox, you don't put clay in it. Okay, clay just ends up underneath all the time because clay is fine. So when dust is deposited, okay, when dust is deposited on surfaces, the really fine stuff can go down between the grainier stuff. Sand is really grainy. Okay, like the particles are thick. If you put it between your fingers, it feels gritty. Okay, if you put clay between your fingers and do this, it feels like flour or cornstarch. It's incredibly fine and almost slippery. So the particles of clay, when it rains, wash down between the particles of sand and end up collecting underneath. So you get this layer of clay underneath. And that happens in all soils, which is why the subsoil is usually made out of clay. Okay, those particles can wash down and end up underneath. Below that, and usually kind of embedded within it, is going to be your decomposed rock, okay, which we call the C horizon or the parent material. Okay, and around our part of the world, the parent material is sandstone. Okay, at least in this part of the world, that's the kind of rock that we have, okay, is sandstone. All right, questions on how that works? Okay, will I ask you about A, B, and C horizons? Yep, good multiple choice question. All right, so the A horizon is, like we said, topsoil, decomposed rock, living organisms, decaying organic material, okay, dead plants and animals, that kind of stuff, okay? And soil is different from place to place. Sometimes topsoil is really dark, sometimes B horizon is really light, okay? It all depends on what kind of rocks are in that area, okay? And as we said, typically in the grasslands or on the prairies, A horizons tend to be very thick because every year the grass dies. It grows anew from below. Right, so all of that leaf material stays there. Okay, also typically in deciduous forests that lose their leaves every year, the soil tends to be pretty thick because there's always this organic material building up on the surface. Whereas in a forest made from spruce trees, like if you go to Kananaskis or Banff, those soils tend to be really thin because there isn't a lot of leaf litter. Right, the needles don't fall off every year. Everyone follow? All right, the B horizon has little or no organic material because it doesn't make it down that far. Rock is less decomposed, so you'll find chunks of rock, pieces of rock, okay? And there's a high amount of clay. We talked about why it washes down underneath, okay? If you go to a place like the tropical rainforest, there's almost no A horizon, almost no topsoil. The trees grow right out of the B horizon. So how does that work? How can you get a big, luxuriant forest with no topsoil? So much water. The topsoil gets washed away. Okay, it's flooded all the time. Topsoil tends to be pretty loose. It erodes really easily. Okay, so if there's a big wind or a big rainstorm or a flood, it's the first thing that gets washed away. Clay tends to cement together, especially when wet. All right, so it doesn't wash away as easily. These plants actually take most of their nutrients right out of the floodwater as opposed to out of the soil. The soil is really only there to anchor them in place. All right, and like we said, the sea horizon is made of decomposed rock, or what we call parent material. So you can see here, this would be kind of the end of the A horizon. Okay, this would be kind of the B horizon in this area. You can see there are chunks of rock in there, but then we get down into this area here where it's mostly chunks of rock. Okay, so that would be like A, B, C. Okay. All right, so the Earth is it's a complex system. We kind of simplify it for our purposes a little bit. Okay, there's inputs of solar energy. Okay, and from it there comes reflected and re-radiated energy, which we call outputs because they're going out of the system. Okay, so we can draw kind of a simple diagram like this: solar input, reflection and emission. Okay, and then emission from the Earth from other things like volcanic eruptions and stuff like that would also result in energy being emitted from the Earth that wasn't actually coming from the sun. Okay, so light that comes in, okay, that's this yellow arrow here, okay, is our shortwave kind of radiation coming in. The atmosphere, okay, it's going to hit the top of the atmosphere, and about 6% of it's going to get backscattered there, and about 16% is going to be absorbed. Okay, you get a little further down, you start hitting clouds in the the lower stratosphere and upper troposphere. Okay, they're going to reflect away about 20% of the light. Okay, we're going to get another 3% absorbed by clouds, and then as we get down to the surface here, 51% would be absorbed. Okay, and another 4% reflected off of the hard land surface if it's not covered in snow. Okay, so we're getting a fair amount of absorption under kind of average conditions. Okay, outgoing radiation includes all of this stuff here that we've included. Okay, we would have kind of radiation and heat that comes from the surface, okay, that are produced more by the Earth, okay, as well as emission by clouds and water vapor, okay, as it condenses. Sometimes that latent heat can actually radiate out into space. Right, so the Earth actually doesn't so much give off a lot of light, but it is reflecting away and allowing a lot of that to escape into space. Okay. All right, questions there? All right, so we're mainly concerned with these numbers here, the ones that include absorption by the Earth, because that's what gets things going. And I say I'm more concerned with these numbers, not their actual values, just that this is happening. You don't need to memorize these values, okay? Just that this stuff is getting absorbed, and that's what gets everything going. Okay, so the main input of energy into our global system is the sun, okay? Everything else is basically so small that if you made a pie chart, it wouldn't even show up. Okay, it would just all look like the sun, and there might be this tiny sliver line that would represent everything else. Okay, so gravity, magnetism, geological forces are negligible by comparison. Where do we see the effect of gravity on Earth? Yeah, we stay around the sun, and one other thing that pulls on the Earth. The moon. What does the moon cause? Tides. Yeah, okay, and tides represent energy. Okay, I mean, there are places on Earth where they're putting turbines essentially in the tidal pools so that as water comes in, it turns the turbine, and as the tides recede, it turns the turbines in the other direction and actually generates electricity, right? That's a use of gravity, essentially turning gravity into a form of energy. Okay? It's not a big thing because you have to have kind of the right conditions for that to work. Like the Bay of Fundy would probably be a decent place because of the massive tidal change that occurs there. Okay? The problem is maintenance. Sand gets in that stuff all the time because of all the movement of the water. All right. And like we said here, absorption is a key part of this, okay, in terms of getting that stuff going. Now, once the energy is on Earth, it can be moved around by 3 methods. Okay, energy is transferred on Earth. So once it's absorbed by the Earth and it's here, it's going to be moved around the Earth by 3 methods. Okay, those methods are conduction, convection, and radiation. How many people have heard of those terms before? Okay, hopefully you remember this is like grade 8 science. Okay, all right. Conduction occurs mostly in solids. All right, and conduction happens because the little particles move back and forth and run into each other. Right? So if you can imagine in this situation here where we've got a solid material, and this person's not very bright, okay? They've got one end of it in the flame and they're holding on to the other end. If this is a metal, how long is it going to take for the other end to get hot? Not long, because metals conduct electricity and heat generally pretty well. Okay, so the particles at this end are going to move a lot. The particles over here aren't moving very much, but because these ones are moving a lot over here, they run into each other and they cause other ones nearby to start moving, and they hit others and start them moving. And it's kind of like if you're in a mosh pit. How many people have ever been in a mosh pit before? Okay. You guys need to get no. Okay. So if you're in a mosh, how many people have seen what a mosh pit looks like? Okay, it's like at a concert. It's the like kind of flood of people that are just moving around. Anyway, okay, if you're in one of these, right, people are jumping around and moving and whatever. Okay, if you're in the middle, you get moved around, bumped around, pushed all over the place. Every once in a while, somebody gets lifted up and they crowd surf, okay, and they end up at the edge of the mosh pit. Okay, and this is a perfect example of, or a perfect analogy for conduction. Sometimes a group of people have so much energy that they actually get lifted and pushed out, okay, and pushed to the edge, right? The rest of us just get bumped around, bumped around. If you're trying to move from the edge of the mosh pit, where there's very little movement, to the middle, it's like a salmon swimming upstream, okay? You have to work very hard because as you move closer, there's more movement and there's more people trying to kind of keep you out, so to speak, all right? Near the source of the flame, the particles will move a lot and they'll be transferring energy to others. Okay? And eventually that flow will get to the outside. Everybody all right with that? Okay, so conduction only happens in solids because it depends on the particles being right closely packed together. Okay? Conduction doesn't work in a gas where there's huge spaces between particles or in a liquid where there's moderately large spaces between particles. Okay? They have to be able to run into each other all the time, and that'll only happen in a solid. Right? So is conduction something that's going to transfer energy on a global scale? No, because it only works really well over short distances, okay? And only in certain materials, solids. Right? So it's not going to play a big part. Now, the biggest one is this. Convection. Okay? Convection happens in fluids. That's liquids and gases. All right? So if you've got like a heater, okay, you've got hot air rising above the heat source, cool air descending, okay, and it gets this current going. Okay, a convection current. If you have a convection oven at home, it's got a fan in it that keeps the temperature of the inside of the oven uniform as opposed to having a hot spot near the elements and cool spots away from the elements. Okay, so the convection, the fan, essentially keeps the air inside the oven moving, right? Your furnace does the same thing. Okay, your house is designed to use convection currents to transfer energy from place to place. On the main floor of your house, where are the furnace grates? Mm-hmm. They're on the floor. Why are they on the floor? Because heat rises. The coldest air is near the floor. So we want the hottest air, the stuff that's coming from the furnace, to encounter it first. Okay, hot air is going to rise past that stuff, okay, go up toward the ceiling, and cold air is going to descend and come right back down over the furnace vents where there's hot air coming out. Okay, so we get this convection current happening. Okay, in your basement, unless you have in-floor heating, okay, you'll probably notice that your basement is colder. Right? All the cold air descends down to the basement, and the worst part of it is your heat vents are probably in the ceiling in the basement if you have a developed basement, okay? And they're trying to blow hot air downwards, which is totally against the way it's supposed to go, okay? But what can you do? You can't run heating ducts through concrete. Right? It doesn't work very well unless you have in-floor hot water heating, and then you get radiant energy coming from the floor. All right, so these are the three methods of heat transfer: conduction, convection, radiation. Convection is the most important for moving energy around on Earth. It's what we call wind. Okay? Wind is the movement of a fluid, our atmosphere, the gases in our atmosphere, because of differences in temperature. Right? Obviously, then, the equator is the warmest place. It's receiving the most intense direct sunshine. Hot air rises from the equator, cool air rushes in from the poles to replace it, and we get these convection currents happening, which is what I'm going to show you, pardon me, in the next lesson. Okay? If it wasn't for convection and the moving of air, okay, the equator would be brutally hot and inhospitable, and the poles would be brutally cold, more so than they are now, and inhospitable. And there'd be this narrow band on both sides of the equator that would be habitable on Earth if it were not for convection. Okay? The air's got to move, it's got to move around. Okay, and of course we're seeing that right now. We're getting lots of air movement the last few days, right? I think today's the first day we don't have a wind warning, although I'm sure we'll get one later, okay? Because they already have one down south of us, right? We've had these extreme changes in pressure and changes in temperature that are causing air to move rapidly. All right, now for radiation, okay? Radiation is also very, very important, but not in terms of transferring energy once it's here. It's for getting it here. Okay? The only way energy gets here from the sun is by radiation, because radiation travels by waves and doesn't have to have a medium in which to move. Okay? Convection doesn't work outside of the Earth's atmosphere. It requires matter to move. Radiation doesn't. Okay? So radiation can travel through the vacuum of space, okay, from the sun to the Earth. Right? Can radiation travel through the Earth's atmosphere? Yes, it does. Okay? It does all the time. You're relying on it right now to see what's on the board. Okay? There's radiation coming from this projector, reflecting off the smartboard and going to your eyes. Okay? It's radiation that's visible light, doesn't hurt you, okay? But it's what our eyes can detect. Okay? There's also radiation coming from here in the form of heat. Okay? I know if I stand under this, it's a lot warmer than if I stand over here, right? That's not energy that we can see, but it's still radiation. It's waves, heat waves, coming from a hot object. Everybody follow there? Right? So radiation is where we get the heat from, and then convection is the most important way of moving it around. Right? Conduction can move it around as well, but not on a global scale. All right. Okay, how many people have been to the ocean before? All right. What do you feel in the morning sitting on the beach? You love the sound of the beach in the morning. Okay, what do you feel in the morning? Is that what you said? Oh, you've never sat on the beach in the morning. Okay, well, there's usually a breeze coming off the ocean in the morning. It's called the sea breeze. Okay, had that experience? You kind of mumbled. I couldn't understand what you're saying. Okay, all right. So in the morning, what we have is this. We have the ocean, and we have the land. With a Charlie Brown Christmas tree on it. Okay, now, because the land is darker than the ocean, its albedo is lower, so it absorbs more energy than the ocean. That means that the air above the land rises. If that was all that happened, it would create a vacuum here. We don't want that. Okay, so what happens instead is cool air comes in off the ocean to replace it. Okay, now that hot air can't fall back down to this spot because cool air is rushed in to replace it. Okay, so essentially what we get is this air cools and moves, and it starts this cycle. Okay, this is a convection current. Right, it's what essentially helps to transfer energy by radiation. It's why we feel a cool breeze coming off of the water. It's this stuff moving in to replace the hot air that has risen. Okay, that's what creates wind. That sort of makes sense? Okay. In the evening, it's the opposite. Okay? In the evening, we get what's called a land breeze, which is now air moves out to sea because the sea holds its energy better than the land does once the sun is gone. Okay? And so this ends up being warmer. Hot air rises over the ocean, cool air blows out to sea, okay? And you get this land breeze instead. Yes, some. But remember, as it goes up, it cools as well, right? So it's not really hot when it gets back over here. Okay? During the day, this stabilizes and the wind stops, right? Until nighttime happens, and then it reverses itself. All right. Now, this latent heat thing that we talked about is also really important. Okay, so water condensing in the atmosphere releases latent heat. Okay, and we said that was important. That warms the surrounding atmosphere. In the sea, currents transfer energy, okay, as does evaporation and condensation of water. All right, so if we look at the various states of water, if I have ice, okay, and I add energy to it, it will increase in temperature to 0, and then it will melt. If I keep adding heat, the water will get hotter and hotter until it gets to 100 degrees Celsius, at which point it will evaporate. Okay, and then if I keep adding heat to that, the steam will get hotter, right? But anytime there's a change in state, so these two places here, that's where latent heat can be either taken in or released. All right, we're usually concerned with the released part. It's moving in from somewhere else and representing a transfer of energy to a new place. Okay, so that's a hydrologic transfer. That happens within the hydrosphere. Okay, this latent heat thing is a hydrologic transfer. Okay, lithospheric transfers, like we said, the lithosphere doesn't play a big part in transferring energy. Okay, for the lithosphere, its big role is the formation of soil, the growth of plants and animals. Okay, that's essentially taking the solar energy and turning it into chemical energy and starting those cycles there. Okay. All right, so big things from this lesson. Okay, we've got to understand those three methods of heat transfer. Okay, so conduction, convection. That's an N and a V. I should have separated them better. Okay, and radiation. Okay, related to these things was this. Okay, albedo and radiation go together. This influences how much of this gets absorbed or reflected or used. Okay, and then once this is determined, that then this can get going. Okay, this is going to be winds, okay, etc. All right, latent heat is also another one. Okay, that's the hydrosphere. But that latent heat still requires this in order to make it work. Okay, just because the hydrosphere can absorb energy and turn it into latent heat isn't enough on its own. The atmosphere then has to move that water vapor from one place to another to make that transfer happen. Right, so those are the big things out of that. Oh, sorry, the other big thing would be this: absorbed, reflected, and used. Okay, but those are the three things that can happen to light from the sun. All right, questions on any of that?